Hello and welcome back. Math 60. This is our PowerPoint number 6, but this one's related to section 2.1 dealing with formulas. So let's begin by defining a formula. A formula is an equation. We just learned how to solve equations, chapter 1, that contains two or more variables. The difference here in this section is that we're going to have two or more variables. The other equations we solved had just a single variable. And formulas are used in many fields actually. They're used to find the perimeter or area or volume of different geometric shapes. They're used to find in the area of finances at least, to find interest, compound interest you pay and earned. Formulas can be used to calculate the velocity of a car, to calculate the average test score. So we use formulas all the time in mathematics and real life applications actually, and you'll see a variety of those. The guidelines to solving a formula are going to sound very similar to those that we learn to solve equations, because that's essentially what we're doing. The formula is an equation and we're solving for certain components. So first of all, we use the distributive property to remove any parentheses or grouping symbols. If there are any fractions, we strongly suggest that you multiply both sides of the equation by the lowest common denominator. That helps clear the fractions. We always, when given the chance, we want to combine like terms, because that simplifies our equations by combining things up. And then we apply the two rules that we learned. First, the addition property. If we need to get rid of any one term from one side of the equation, we know that we can add or subtract anything we want from both sides of an equation as long as we do the same thing to both sides, which is what they're reminding us here. We can add anything we want to both sides, but we can also multiply. And by that, we can also divide, because we can multiply by fractions. So we use all the properties that we learned to solve equations, and we're going to apply them here with formulas. So what's a formula? Here's an example. This first formula, as you can see, yes, it's an equation. It says solve the equation 4x plus 3y equals 15, and we're solving it for x. And it's really important to identify what variable we're solving it for. So to begin with, is this a formula? It is a formula because, as you can see, there are two different variables, in this case x and y, but we're really only interested in solving it for x, which means when all is said and done, we want to have x by itself and everything else to the other side of the equation. So how do we begin by doing that? Well, if we're solving for x, and I want to get that alone, we can see in this other second term there are no x's, so we can take that entire term and move it to the other side. And how do we do that? Of course, we learned that last chapter by just, in this case, subtracting. We do the opposite. Since we're adding 3y, let's subtract 3y from both sides. And when we do, this whole term goes away, and we're left with 4x equals negative 3y plus 15. Some of you at this point might say, well, wait, couldn't we or shouldn't we write that as 15 minus 3y? You certainly can. You certainly can. It's not, it's the same thing. However you have it written, it's acceptable, and both are fine. Now we're solving for x again. We're not quite there, almost there. We have this pesky 4 we need to take care of. So since they're being multiplied, 4 times x, in order to get rid of the 4, we do the opposite, which is divide. So we divide both sides of the equation by 4. And we do that because we know that 4 divided by 4 is 1, and 1 times x is x. So we've solved for x by getting it by itself. And when we look at the right-hand side, if you left the right-hand side as negative 3y plus 15 divided by 4, you'd be right. That's acceptable. As we move towards chapter 3 and working with lines, it might be advantageous to see this denominator 4 and split these terms up by dividing each of them separately by 4. Therefore, you get negative 3/4 y plus 15/4. And again, if some of you looked at 15/4 and wanted to write that as 3 3/4 as a mixed number, that's fine too. So really, any of those three outcomes is acceptable. Let's look at something extremely similar. And at any time in these videos, it's a good chance for you to practice. So if you'd like, you can pause this video now and try to solve this equation and then turn it back on and see how we do it. The difference here is that we have the formula 4x plus 3y equals 15, but now we're solving for y. Always keep your eye on the variable you're going to solve for. So here's the variable we're solving for, which means we need to get it by itself. So we, like last example, begin by getting rid of the term that does not have a y in it. So we subtract 4x from both sides. And then solving for y here means that we got to get rid of the 3. So we divide both sides by 3, and we come up with our final equation. Again, if you left it in this form, you would not be wrong. There's a convenience to splitting it up, especially in this case, because 15 divided by 3 was 5. Cleans things up a little bit. But here we've solved for y. So let's try just one more that's a little bit more involved, maybe even a little bit more intimidating. And this is a formula that has a direct application, which you probably are not aware of. It says solve s equals 2 pi r squared plus 2 pi r h, and we're supposed to solve that for h. And if you look closely, the only h that exists is sitting right out here to the very end. This happens to be a formula to find the surface area for a cylinder with a top and bottom. You don't need to know that ahead of time. There's no need to know that. What we are interested in is solving this equation for the variable h. Again, the first term on the right hand side doesn't even have an h, so in solving, the very first thing we're going to do is just subtract that from both sides, and in doing so we move that whole term to the left. Now we're still interested in solving for h, which means we need to get rid of the 2 pi r, but since it's all being multiplied together, we can easily get rid of that by dividing both sides by 2 pi r. So when we do, we get our result, our finished solving for the variable h. H equals s minus 2 pi r squared divided by 2 pi r. And if you left it at that, you would be just fine. If you wanted to try and clean it up, you could. You could take our result and, like we did before, realize that this denominator is being divided into two separate terms. So rewrite it to see that it's being divided into two separate terms. And the fairly clear advantage to doing this is that the 2's and the pi's cancel in the second term, and we get a different looking result. These two fractions look different, but both are acceptable and both are correct. They both equal h. Now let's get to an application problem. We'll finish with this application problem. We're going to begin by using a fairly well-known type of problem, but also that requires a formula that maybe you're already familiar with, but you and I need to be familiar with in order to solve this, and that's distance problems. We're going to start by recognizing that the relationship we need to be aware of is that the distance equals rate times time. Some of you may have seen this written as d equals rt. Distance equals rate times time. So for example, if you travel at a rate of 60 miles per hour and you're traveling for 2 hours, the question says, how far have you gone? Well, distance equals rate times time. Our distance, how far have we gone, would be 60 miles per hour times 2 hours. So 60 times 2, our distance would be 120 miles. So my calculation tells me that it's 120 miles. Yours probably did too, and that's the correct distance. So we want you to be familiar with distance problems, but specifically this relationship, distance equals rate times time. In a traditional application problem, Pat drove 3 hours to attend a meeting. On the return trip, his speed was 10 miles an hour less, and the trip took 4 hours. What was his speed each way? Now, when we approach not just this, but all application problems, we kind of have a plan of attack here, and I suggest we get a little organized by, number one, let's define our variables. Our variable is going to represent what we're looking for. In this case, what his speed was. So I'm looking for his speed, and we do have to make sure that we find it for each way. We set up an equation. Students often hop to number 2 first. They want to look for that equation, but we get our equation from first defining what we know. Then after we have our equation, we of course solve that equation, which you have become quite good at. And then third, we want to state the solution with a complete sentence. And the importance of this is in part making sure that we have answered the question that's being asked completely and clearly. So let's do this. Pat drove 3 hours to attend a meeting. On the return trip, his speed was 10 miles an hour less, and the trip took 4 hours. What was his speed each way? So first of all, let's get organized. Distance, rate, and time problems, almost all these type of problems would really beg to have some kind of picture or graph or some way for us to organize our information. Some people like to draw a little graph where we start, at city A and go to city B. The other way to organize our information is using some kind of table. In this case, we have a table broke into the distance equals rate times time, distance, rate, and time for the two trips, the trip going and the trip returning. And really here, we're not at all looking for an equation or solving it yet. We're looking just to get organized. So first, let's write down what we know. We know that on the trip going to the meeting, it took 3 hours. We also know coming home, it took 4 hours. So I don't have to worry about keeping hold of that. I'm just writing down information that I know from the problem. Now let's define our variable. We're going to let x be the speed going to the meeting, how fast he drove to the meeting. So we're going to put that under rate in this table. So now we know going to the meeting, we know his rate, and we know the time. Now if x is the speed going to the meeting, then we're going to let x minus 10 be the speed returning from the meeting. Remember, it said it took 10 miles an hour less. Therefore, if x is how fast he drove to the meeting, then x minus 10 would be the rate or speed that he was driving home from the meeting. Now we learned that distance equals rate times time. Rate times time. So to calculate our distance, we're going to multiply the rate and the time, both for going and for coming home. Now here's where we have to get a little creative and look a little deeper into the problem, into things that maybe aren't literally written. And that is, we've got Pat driving presumably from home to a meeting and then from the meeting home. It does not state it literally that they took the exact same trip, but it is assumed or implied, which means that going to the meeting, the distance is the same as going back home. So we have to recognize that the distance going equals the distance returning, which means that the distance going, the 3x, has to be equal to the distance returning, and there's our equation. So what's left then is to take the equation that we have created, we end up with 3x equals 4x minus 40. Distributing that 4. Now in solving this, of course, we have x on both sides. Since x is by itself here, I'm going to move the 4x to the left side. So I'm going to subtract 4x from both sides. So 3x minus 4x is negative 1x. And on the right-hand side, this goes to 0, of course, and we're left with minus 40. Now, I don't want to know what negative x is. I want to know what positive x is. So I'm going to divide both sides by negative 1 or multiply both sides by negative 1. Either works. What it ultimately ends up doing is just changing the sign of both sides. So x equals positive 40. And since x was my speed going to the meeting, Pat drove 40 miles an hour to his meeting. Now remember, x minus 10 was his rate or speed coming home. So that means 40 minus 10, his rate or speed coming home would be 30 miles per hour. And that is home. So we were able to solve that equation, and now we get to, summarize things. We want to interpret the results. It said here, and it's given us two choices. Patrick's speed was 40 miles an hour going to the meeting, 30 miles an hour home, or Patrick's speed was 30 miles an hour going to the meeting, 40 miles per hour home. Now, since we were so good at defining x as being the speed going to the meeting, that would be the one that we would want to choose for sure. So let's summarize here. When we're solving formulas, the formulas are equations with two or more variables. Oftentimes these equations we may or may not be familiar with. Some that you probably have seen before or might be familiar with, we just want to refresh your memory, come from geometry, such as the perimeter of a rectangle. The perimeter P equals 2 times the width plus 2 times the length. It's a formula you might be familiar with. I'm sure many of you are familiar with how to find the area of a rectangle. Area equals length times width. So you see, these are just examples of formulas that are used regularly. You might encounter these, probably will. And then area of a triangle. Area equals 1/2 the base of a triangle times the triangle's height. So here's some geometry formulas that you've probably seen, you may encounter. And then in summary, then a formula is an equation that contains 2 or more variables. Solving a formula, then we would want to remove any grouping symbols by using the distributive property. If there are any fractions, we want to multiply both sides by the least common denominator in order to clear the fractions. Then at any time we have the opportunity, we always want to combine like terms to simplify. And then lastly, we want to then apply either the addition property of equality or the multiplication property of equality to get the variable we're asked to solve for by itself. Well, I hope that helps. I think you're ready to tackle section 2.1, dealing with formulas.